Sagnik, you can share the presentation now, and then
Okay.
you can just check if it's working properly. Okay. Okay, so maybe we should start. Welcome everyone. So this is the third talk of our seminar series, and Sagnik from IACS today will be talking about creation of superposition of unknown quantum states. And without further adding anything, over to you, Sagnik.
Thanks, Anirbanda. Okay. Hello, everyone. Today, as you can see, I'm going to discuss this topic, creation of superposition of unknown quantum states. So we are all familiar with the phenomenon of quantum superposition, theoretically as well as practically. So it is the chief distinguishing feature of quantum mechanics, that superposition of states, that an object can exist in a superposition of states. This allows for several intriguing phenomena which are not allowed by classical physics. So the question which I'm going to deal with, which I'm going to discuss today, as has been discussed in recent papers, that if we want to experimentally generate a particular superposition, so can we generate any superposition we like? And what are the restrictions on that? For the discussion, the discussion will take place in using the formalism of quantum information theory, to be specific. So in quantum information theory, the basic unit of quantum information theory is the qubit, where it can exist in either of the two states, orthonormal basis state 0 or 1. In this respect, it is similar to the classical bit, but as it's a qubit, it can also exist in a superposition of the two orthonormal basis states. So we are going to deal with superposition of qubit states and try to understand what kind of restrictions are there on generating arbitrary superpositions of different qubit states. One more thing, as we all know, when we measure a quantum state, it collapses to particular basis state in which basis the measurement is taking place. So only after measurement we come to know of the outcome, and it changes the state irreversibly. So when we will be dealing with creating these superpositions, we will be dealing with the question of generating superpositions of unknown quantum states. The states are not known to us. So can we generate arbitrary superpositions of unknown quantum states? So let's move ahead with the discussion. So before going into the discussion, the main part of the discussion, let me start with the no cloning theorem, which is a very important theorem of quantum mechanics. So the no cloning theorem forbids the creation of identical copies of an arbitrary unknown quantum state. So actually, this is a very important principle because the distinction which we have between the classical world and the quantum world, the no cloning theorem protects the distinctiveness of the quantum world. If we could have made arbitrary number of copies of an unknown quantum state, then by doing repeated measurements on the various copies, we could have guessed very well what the original state was. So the collapse from a superposition state to one of the basis states, this non-intriguing feature would have been modified to a great extent if we could have made arbitrary number of copies. But the no cloning theorem prevents this from happening. So let's take a look at the very short proof of the theorem. Let's say we have an unknown quantum cloner with two slots where two states are inputted. So one is the ancilla state chi. It is the starting state of the machine, and let's say we want to copy the state psi. So psi and chi are the input states, and the output generated is 2 copies of psi. So let's say the quantum cloner works perfectly for this state. It perfectly produces a copy of this state. Then let us also assume that the quantum cloner also works perfectly for the state phi and the states, and also generates a copy of the state phi. But it can be seen, even if we assume these 2 conditions, then if we want to copy a state which is a superposition of the 2 states psi and phi, then this is prevented by the linearity of quantum operations. This same machine, as can be seen in this equation, this same machine which will produce the output will not give us the desired output of another copy of this superposed state. So the basic linearity of quantum operations prevents us from cloning an arbitrary unknown quantum state. So in this proof, the linearity of quantum operations has been used, but another proof can also be given where we assume the quantum cloning machine to be unitary. So if we assume the unitarity of this machine, then it can be easily proven that a particular unitary quantum cloner can copy states which are all orthogonal to one another. But those states which are not orthogonal to those set of states which that quantum cloner can copy, such states cannot be copied by using that particular quantum cloner. If we use the condition of unitarity, this restriction will appear. But this proof based on linearity is more general. So now, what I want to discuss, let's say the question of superposition, let's say we are now trying to construct a unitary quantum adder which generates a superposition of 2 input states. So let the 2 input states be psi and phi, and then the output will be proportional to the superposed state plus some ancilla qubit that is generated also. And in general, this ancilla qubit, this output ancilla qubit may depend on the input states. But let us make a simplifying assumption that this ancilla qubit is independent of the input states. And also let us consider the case where the 2 states which we are trying to superpose, they are both the same, psi equals to phi. Now, if we substitute this into the expression, we see that we are entering basically 2 copies of psi, and we are getting as an output as expected psi and the ancilla qubit chi. But we know that unitary operations are reversible. So if we reverse this map, then what does the map look like? From psi and chi, we are generating 2 copies of psi. But this particular operation, as we have already seen, is forbidden by the no cloning theorem. So from this, we can conclude that there can be no such unitary operation which will allow us to generate superposition of arbitrary quantum states. So the existence of a universal unitary quantum adder is forbidden. So the question which remains to be investigated is then, can a non-unitary quantum adder exist, which if supplied with 2 unknown quantum states can produce a superposition? So this will be the topic of the rest of the talk. Can such an non-invertible universal quantum adder exist? As it is non-invertible, it is also non-unitary. So before discussing the various proofs and statements and results which are there in the paper, I have to introduce some basic preliminary concepts. So I will discuss the density matrix formalism, the block sphere representation, and in some more detail, I will discuss the quantum operations formalism, which will be very important to comprehend the proofs of the paper. So let's go ahead. So when is the density matrix formalism useful? So a quantum system is described by a particular state vector. So if we are dealing with such a quantum system where we do not know what is the state vector of the system, but we know that there are a set of states in which the quantum system can be with some probability, then the density matrix formalism becomes useful. Then we can represent the system as a statistical mixture of these states with the respective probabilities. So the important properties of this density operator is it is self-adjoint, positive, semi-definite. That means all its eigenvalues are non-negative. This has to be because the eigenvalues are basically the probabilities of being in particular states. And as they are the probabilities, their sum should be 1. Therefore, trace of rho is also equals to 1. So if the state vector of a system is precisely known, then we say that the system is in the pure state. Otherwise, it is said that the system is in a mixed state. Now, for given an arbitrary density matrix, where from the density matrix we cannot directly recover the state vector. So if we are just supplied with the density matrix and try to check whether this density matrix represents a pure state or a mixed state, then this is the check. For a pure state, rho square will be equals to rho, and therefore automatically trace of rho square will also be equals to trace of rho, which is 1. And for a mixed state, rho square will not be equals to rho, and trace of rho square will be less than 1. This is the basic check which can be done to get an idea whether it is in a pure state or in a mixed state. Or now in the density matrix formalism, the unitary evolution, any type of unitary evolution, and also the time evolution is represented in this manner. So each of the state vectors, the Kate vector and Bra vector, on them the unitary operator acts. So we automatically get this formula. And to describe measurement sum of various projectors multiplied by the corresponding eigenvalues of the operator. And then the probability of getting a particular result AM is trace of PM into rho, where PM is the particular projector corresponding to the eigenvalue AM. And then it can be easily shown that using this formula, the expectation value of that operator in that particular state rho is trace of A rho. And if the measurement is carried out, the post-measurement state is basically PM rho PM. And in the denominator, that trace of PM rho, that is basically a normalization factor, which ensures that the trace of the post-measurement density matrix is 1.
Hi, Shagnik.
Yes.
Can you go back to the previous slide, please?
This one?
Okay. Yes, this one. So here you have written that you need the spectral decomposition of the operator. So there is this choice of basis which is really important here. If you are dealing with these eigenvalues, right? And like if I just write some operator which is really not written in this eigenbasis, then does this measurement scheme still work? I'm just asking. I don't know. I was reading something.
Well, so you are in general what we do. We first choose an orthonormal basis, and then represent the operators in that basis.
Right.
So after doing that, then it's the normal procedure what we do. Then we find out from that matrix representation the eigenvalues and eigenvectors. And then from the eigenvectors, we can calculate the respective projectors. and then multiply them with the corresponding eigenvalues, we will get the representation, corresponding representation. And after measurement, it will obviously collapse to one of the eigenstates. So then that ambiguity about the starting basis will go away.
Okay. Okay. Now. So you're saying that this collapse will happen, right? And then you're saying this ambiguity will go away. This ambiguity, by this ambiguity, you mean that I can choose any basis. Let's say I was working with a Z basis, and then I'm like, no, I'll work with SX basis. So you are talking about that ambiguity will just go away after the collapse. Is
Yes,
that
that will not matter,
so?
because
You're
it will collapse to those particular eigenstates, right? So the matrix representations of the particular projectors may be different
yes,
for a
exactly.
different starting basis. But
Yes,
the results which you will get, the probability or the expectation values, these will be the same.
okay, right. You're dealing with expectations values, right? Okay, I understand. Okay, thank you.
Okay. So one of the most useful properties of this density matrix formalism is this, that we can calculate something known as the reduced density matrix. Now, this is very important because let's say we consider a system composed of two parts A and B, and then we know the state vector psi for the whole system. So as long as we are interested with the whole system, uh, we can use the state vector psi and carry out all the necessary calculations. But let's say we are interested only in a particular subpart A of the system. Then what can be done? Because the state vector formalism doesn't give us any scope to deal with a part of the system. We cannot assign an arbitrary state vector to a part of the system, even if we know the state vector for the whole system. So if the various subparts are in a product state with each other, so psi1 Kronecker product, psi2 Kronecker product, psi3, then it's all right. Then we can just deal with psi1. But in general, this cannot be done. So the density matrix formalism allows us to do just this. So we start with the pure state of the whole system, and then by an operation known as the partial trace, we trace out that part of the system with which we are not interested. Basically, we treat it as an environment. So this partial trace operation is extremely useful, and then the density matrix which we obtain after tracing out, let's say B, the part B is traced out, then the density matrix rho A, which describes subsystem A, is known as its reduced density matrix. And then the measurement formalism and evolution, which we discussed in the previous slide, that can all be carried out with rho A. Now, if you, where the measurements will only be on the system A and not on the whole system. So this formalism is very useful, and this reduced density matrix and partial trace will be used later in the talk. So that is all about density matrix which we will require. Now let us move to the block sphere representation. So as I showed you in the first slide, that a qubit state can be written as a superposition of orthonormal basis states 0 and 1, and with the respective normalized coefficients. So we can choose a particular parametrization for these coefficients, cos theta 2 and e to the power I phi sine theta by 2. So that obviously, as can be seen, respects the normalization. And using this representation, using this expression, we can give a geometric representation of a qubit state, and that is known as the block sphere representation. So which is shown in the adjoining figure. And so this is a unit sphere, and the state of a qubit lies somewhere on the surface of this sphere, and it is parametrized by the two values theta and phi on this three-dimensional sphere. While writing an arbitrary general state, we can also add an overall global phase e to the power I gamma, but as the global phase does not directly affect the measurement statistics, it has been omitted. But the phase e to the power I phi, which is the relative phase, is very important as it affects the measurement statistics. Now, this distinction between the global phase and relative phase will be very important in the later discussion, as the difference between the two phases will constitute an important part of the results, will lead to the important results which will be discussed with respect to the possibility of superposition. So there in the previous slide, we saw how to represent the state in the block sphere representation. Now, if we go over to the density matrix formalism, then using this particular result that any 2x2 Hermitian matrix can be written in a unique way as a linear combination of the 2x2 identity matrix and the Pauli matrices with real coefficients. So using these results, as the density matrix is a 2x2 identity matrix, we can expand the density matrix in this basis, as has been shown. Now, note that overall coefficient of half that is there to ensure that the trace of the density matrix is 1. As all the Pauli matrices are traceless, and the trace of the identity matrix will only matter, which is equals to 2. To bring that down to 1, the factor of half has been included, so that we get a valid density matrix. We also saw that an important property of the density matrix that it is positive semi-definite, and that can be ensured by checking whether the determinant of rho is non-negative. So that is the particular form we get 1 by 4 1 minus mod p square for the determinant of rho to be positive, non-negative. And so we get a condition that mod of p square must be less than or equals to 1. If it is 1, then the determinant of rho will be 0, which is also allowed. It basically has to be only non-negative. So this vector p, which must have a norm less than 1, this can be used to parameterize the various possible states of a qubit. So,
sorry, I have a question.
Yeah.
So can you go back to the previous slide? Yeah. So what will happen if two eigenvalues are negative, any even number of eigenvalues are negative, then still you can have positive determinant?
Yes, then we can have positive determinant, but we are dealing with a 2x2 density matrix. So we basically have two eigenvalues. Then even if we have two negative eigenvalues, we will have a positive determinant. But in that case, trace of rho will no longer be 1. So we cannot have two negative eigenvalues.
Okay, for a 2x2 matrix, okay. Okay, thank you.
Okay, thanks. Now, the mod of p must be less than 1. So this condition, this vector p, is basically parameterizes the various possible density matrices and the various possible states of a qubit, which are various different points on the block ball. That is the sphere and also its interior. And the boundary of the block ball is basically known as the block sphere. Now, the density matrices, as you can see, which correspond to the boundary, which is given by mod of p equals to 1. So, in that case, the determinant of rho turns out to be 0. Now, as I said, the trace has to be 1. And if the determinant of rho is 0, one of the eigenvalues has to be 0. So, the eigenvalues in this case are basically 0 and 1. And I also told earlier that for pure states, the density matrices satisfy the property rho square equals to rho. And so rho square minus rho must be equals to 0 according to the characteristic equation. And so the eigenvalues will also be 0 and 1. So from this correspondence, we can conclude that the boundary of the block ball, that is the block sphere, it corresponds to pure states of a qubit, which can be described by state vectors, and the interior of the block ball, that corresponds to mixed states of the qubit. So this is also an important result. So that is all which I wanted to say about the block ball. Now let us go into the quantum operations formalism. Now, why do we need to discuss this quantum operation formalism? This is also related to the particular question which I discussed, that when we want to describe only a subsystem of the whole system, then basically we need some new formalisms. The state vector formalism which we usually learn is insufficient. So by this state vector, we can basically study the evolution, measurement, and other properties of a closed quantum system that practically has no environment, does not interact with any environment. But when we are dealing with open quantum systems which have an environment, then that continuous interaction with the environment has to be modeled. But we are, at the end of the day, only interested in the system. So this particular tracing out of the environment is a very important issue. And in that case, just as the reduced density matrix formalism is useful, so the quantum operations formalism is also very useful for dealing with open quantum systems. And this formalism is also, let's say, at the beginning, a bit abstract, but precisely due to its abstractness, it is very useful and general. So it is basically described as a map which maps the input quantum system input state rho to the output state rho prime. And as I said, the whole system plus environment, if we take this as a whole system, then that whole system is a closed quantum system which undergoes unitary evolution and unitary transformations. And so let's say that whole system, rho, Kronecker product, rho environment, that whole system undergoes some unitary evolution. And then to get the state of the principal system with which we are interested, we have to trace out the environment. In this representation, a simplification has been made. It has been assumed that initially the principal system and its environment are in product states. They're in a product state with each other. That may not be true. They might be entangled with each other as well. But in that case also, this formalism works. Basically, we have to do whatever we want. The whole evolution has to be performed on the whole system. And then finally, the environment is traced out. So let's just...
Hi, Shagnik.
Yeah.
So this U and U dagger, right, in the last slide, so does it have a specific form of some sort when it is working on the product space of rho cross rho environment? Or
not
unitarity is
necessarily.
just-
I mean, it might have some
Right.
simplifying cases, but I am not aware.
So unitarity is only required for this. Nothing.
Yes,
Nothing.
because evolution of a closed system will always be unitary.
Yes. Yes. Okay. But like for this formalism to work, there is no other further restrictions on U or U dagger, right?
No.
Okay. Okay. Thank you.
So let's just go into this in a bit more detail. So let's say we choose an orthonormal basis EK for the environment, and let the environment start out in this particular state E0. So then, as you can see in the next equation, what was shown in the previous slide is carried out. The unitary evolution is carried out, and then using the vectors EK, the environment is traced out. And this, as you can be seen, can be represented in the form EK rho E dagger and then summation over all the basis states. Now, every quantum operation can be represented in this particular form. Here it has been derived under certain simplifications because that is easier, but every quantum operation can be represented in this particular form, which is known as the operator sum representation. And the particular operators Ek are known as the Krauss operators. Now, let's say how to deal with measurements in this formalism. So, we perform a projective measurement on the environment. So, a measurement on the environment will also lead to collapse of the whole state. So, in that particular basis Ek, we choose any of the particular basis vectors and perform a projective measurement. So, what is the probability that the system will collapse to that particular state corresponding to Ek? So here, first we calculate the post-measurement state in a similar fashion as was shown in the previous slide. They take the partial trace and see the normalized post-measurement state is Ek rho, Ek dagger, and then there's the factor in the denominator, which is the normalizing factor. And then to get the probability of the outcome, as was shown when I discussed density matrix in general, we have to take the product of the projector with the state and then perform a trace. Now, this trace is over the whole system and not only on the environment. The environment has already been traced out, and that gives us the formula of trace Ek rho, Ek dagger. So we saw we have a set of Krauss operators Ek, which correspond to particular outcomes of measurement. So we get a particular outcome K. So the probability for getting that particular outcome is given by trace Ek rho, Ek dagger. And so the whole post-measurement state, if we consider that the measurement, if we consider all the possible outcomes of the measurement, then that state is represented by an ensemble of post-measurement states where each rho K is the particular post-measurement state corresponding to one particular outcome, and Pk is the corresponding probability, and sum over K then gives us the whole ensemble, the whole range of possible outputs which we can get under performing this measurement. Another important property of any quantum operation is that a quantum operation, first of all, it must be a positive map. Because as I said, that density operator is always positive. Yes.
Sagnik, you are assuming that at starting point, your system environment is in a pure state E0, right?
No.
Then you should have the summation over E0 state or something like that.
In this case, I'm assuming the environment is starting out in a particular pure state, E0.
Yes, yes.
But
That's
the
okay. But
the principal system, the system in which you're interested, that can be anything. Mixed state, pure state. That there is no restriction on that rho.
okay, that's okay.
And this also is done because I'm giving a very simple presentation. The results are valid for all possibilities. Here it is an assumption that we are starting out with E0, E0.
Okay, for general case where our environment state is in mixed state, so for that case, this expression will be valid, right?
Yes, it will
Okay,
be.
thank you.
So, as I said, the density matrix is a positive operator. It is positive semi-definite. And as the output of a quantum operation is also a density matrix, so the quantum operation must be a positive map. Positive operators must be mapped to positive operators. So that is quite intuitive. But there is also an additional restriction. That is, a valid quantum operation must also be completely positive. And what does that mean? That the operation must remain positive even when it acts only on just part of the larger system. So let's say EA is a valid quantum operation. Let's say we have a system AB where EA acts only on the part A, while it does not do anything to the part B. Then the composite operation on the whole system is represented by a direct product of the identity operator with EA. EA acts on part A and I acts on part B. So the composite operation is E equals to I plus EA. So even this operation must be positive. So only EA, if it is positive, then it is not a valid quantum operation. It is a necessary condition, of course, but it is not sufficient. For any extension I cross EA, this composite operator also has to be positive. That is the criterion of complete positivity. For example, to give a counter example of this, if we consider that EA is equals to the transpose operation, then transpose operation by itself is a positive operation. If a particular system, a transpose map, acts on a particular density operator, the output density operator is also positive semi-definite. So there is no problem. But if we consider a particular system rho AB and the transpose map is acting only on A while not affecting B, then the output density operator of the composite system, it can be easily shown that it is no longer positive. So the transpose map does not satisfy the criterion of complete positivity. So in
Sagnik,
quantum, yes,
why this positivity is needed?
because rho always has non-negative eigenvalues. So the output state must also be a valid density matrix.
Okay. Okay.
So for any such extension, we have to check whether the particular map which we are using for any such extension, it is also remains positive. If it is, then it is a valid quantum operation. So quantum operations can also be classified based on whether they're trace preserving or trace non-preserving. So as I also showed that the trace of rho must be 1. So from that it can be guessed that the output density matrix must also have trace 1. So if we impose this condition, the trace of E rho is 1, then we get a condition on the Krauss operators that summation k ek dagger ek has to be 1. So this is all fine, but in general, the formalism of quantum operations also allows for non-trace preserving quantum operations. So let's take a particular example. Let's say here we have 3 quantum operations, E0 rho, which basically represents a projective measurement which collapses the state onto the state 0. And E1 rho is a particular projective measurement which collapses the state rho onto the state 1. And EC rho is the sum of both these operations. Now let's say rho is the state of a qubit. So if we carry out a measurement in the 0-1 orthonormal basis, it will collapse either to 0 or to 1. So, and this formalism is now so adjusted that trace of a particular quantum operation, as we showed, gives the probability of occurrence of the process represented by that particular quantum operation. So E0 rho, trace of E0 rho gives the probability that the state rho will collapse to the state 0, while E1 rho gives the probability that the trace rho will collapse to the state 1. But as this gives the probabilities, so they must be less than 1, because in general an arbitrary quantum state will have a non-zero probability of collapsing to either of the states 0 or 1. But E0, which is the sum of both these operations, the trace of that is equals to 1 because it encompasses all the possible outcomes. The outcome will be either be 0 or 1. As E0 encompasses both of those, then trace of E0 is equals to 1. So E0 is here a trace preserving quantum operation, while E0 row and E1 row are non-trace preserving quantum operations. For non-trace preserving quantum operations, the condition of Krauss operators is only slightly modified. Instead of being equals to 1, there sum being equals to 1, it is less than or equals to 1. The equals to case corresponds to the trace preserving case. That is basically all about the quantum operations formalism. So just one more important note, the way I discussed quantum operations based on some physical arguments, tracing out the environment, subsystem, etc., that is one way of approaching the whole thing. Another way is a purely axiomatic approach, where a quantum operation is demanded that it satisfies some properties. These are the three important properties. One, we already discussed just now, that trace of 0 will lie between 0 and 1. Corresponding to that, the probabilities will be calculated. And the normalized post-operation states, in this case, will have a factor trace of 0 in order to ensure that the output density matrix has trace 1. It also has to be a convex linear map. I'm not going into discussing this axiom because it is a bit complicated and it is also not required for this talk. And it is a completely positive map. So these are the three axioms which are needed to be satisfied by a valid quantum operation. And if a particular quantum operation satisfies all these three axioms, it can be proven that such an operation can always be represented in this form, summation of k, ek rho, ek dagger. So the Krauss representation or operator sum representation is valid for all quantum operations. There are rigorous proofs for all these things. I'm just stating the results. So this basically ends our discussion of the preliminaries. And now I go into the main results which I want to discuss. So I stressed while discussing the block sphere representation that the difference between global phase and relative phase will play a very important role. So here it is. Let's say we have a phase phi which is equals to phi 1 plus phi 2. Now we have two states, psi and phi, and we want a machine which will create a superposition of these two states. Now, the combination of these two states may have an arbitrary global phase e to the power I phi. So, no measurement, as the global phase does not directly affect measurement statistics, we have no way of detecting this overall global phase, which is there in the input states. And now, so you can see e to the power I phi psi phi can also be written as e to the power I phi 1 psi into e to the power I phi 2 phi, where phi is equals to phi 1 plus phi 2. Now, let the operation S act on these two states. The target of operation S is to generate a superposition of the two states, psi and phi. So what we will get, it has been shown where chi, as was previously the case, is an ancilla QV. Now you see, initially e to the power I phi was an arbitrary global phase, which we could not, without any physical significance. But that global phase can split up. We have no control over that. And now, in the superposed state, can sit as relative phases in front of the two components. But this relative phase has direct physical significance. It leads to differences in interference pattern and all that stuff. So but how this entire global phase will be distributed to the two composing parts of the superposition, psi and phi, it's totally arbitrary. So the global phase, which was unobservable, that can be distributed in infinite forms and yield an observable relative phase. So, due to this problem, given to arbitrary input states, it is absolutely impossible to define a unique superposition as the output. So, the machine will produce which superposition. There are an infinite number of varieties. So in this paper, the reference of which is given below, this problem was posed that, and it was concluded that a generic quantum adder is therefore impossible because the output state can never be uniquely defined. But is there a way to go around this problem? Or otherwise we have...
Sorry, Sagnik, so what is the role of this ancilla qubit? I probably missed it somewhere.
Okay, so there is no particular role here. So in all such quantum circuits, what happens that here we want to create a superposition of two states.
Right.
So that will have to be represented, let's say implemented, let's say by 2 qubits. 2 qubits which will then be superposed. Now when they will be superposed, they will be superposed in one particular qubit. That cannot be superposed in 2 different qubits, physically 2 different qubits. So one particular qubit will now embody the superposed state. Now what will the other qubit do? That other qubit which is physically there in the machine, that cannot go away. So according to the mechanism designed, that qubit remains in some other arbitrary state, which is basically the garbage of the output. So that cannot...
Here.
Yes.
Okay, so like for any quantum operation, let's say you're talking about superposition here, I'm talking about something else. Then also you're saying that there will be one qubit which will embody the operation and the other qubit should actually pick up the garbage value or
I mean,
something.
one or more, what is the number?
Yes, one or more, right.
Yes, that depends on the particular, that I also showed in the no cloning theorem.
Right,
There
right.
also, the differences in the no cloning theorem, the ancilla qubit was in the initial part. Because that ancilla qubit also has to be cloned to the other state. There, that was the target. Here
Yes.
in this case, the ancilla qubit is in the output because the operation is basically opposite. So ancilla qubit will be there. That is the physically the garbage qubit, which we do not require. In this case, it is garbage. While in the no cloning theorem, it is, in the cloning case, it is not garbage. In that case, it is important because that qubit will embody the copy of the state. But in this case, this is a garbage qubit.
So,
in the output.
So another follow-up question on this, like, is there any quantum operation which does not require an ancilla qubit, or it is of utmost importance that there will be an ancilla qubit in every quantum operation?
Well, I am not an expert on that. There might be, but in general, because implementing a qubit physically requires resources. So,
right.
In general, an efficient quantum algorithm will be one which will minimize the number of such ancilla qubits.
Okay, I see.
So lesser the number of ancilla qubits, lesser the physical resources required in the lab to implement that particular algorithm. So,
right.
But totally eliminating all ancilla qubits is not generally possible. I mean, in most cases, not possible.
Okay, so that's something interesting. Okay, thank you.
Okay. So how to go around this problem? So before discussing further, I have to introduce some terminology which will be useful in the further discussion. So now we are accustomed to calling the state vector psi as the state of the quantum system. That's what we generally do. But in the rest of the talk, I will switch to another terminology. Psi or phi, such vectors which we want to superpose, I will call them vectors or vector representatives. While the corresponding projectors, ket psi plus psi, those I will call to be states. The projectors will be called states, while the corresponding vectors will be called vector representatives. So one of the utilities of using these projectors rather than the states, rather than the vector representatives themselves, is this: when we are doing the projector, if any arbitrary global phase is there accompanied with psi, that gets cancelled. That's the, as we are having a problem with phase, we want to eliminate arbitrary phases as much as possible to see if we can solve this problem. So the state psi are the vector representatives and the projectors are the states. So p psi will be equals to p psi prime if and only if psi prime is equals to xi multiplied by some arbitrary global phase. So there are an infinite possible number of vector representatives for a particular state p psi which are related to each other by a change of global phase. But we will interpret all of them as the same state as we are considering the projectors to be the states. So now let alpha beta be two numbers. These are basically the two weights with which we want to create the superposition. So let's say the superposed state is now, superposed vector representative is capital Xi and superposed state is P Xi. So capital Xi will be given by n inverse of alpha psi plus beta phi, where n is the normalizing factor. So we have switched from vector representatives to projectors, but this has not yet solved the problem. Because as you can see, if we calculate the vector representative of the from the vector representative of the output state, if we calculate the state p psi, then it can easily be seen that the output state p psi is not a well-defined function of the input states, because it directly depends on the vector representatives of the input states. And as I just showed, that any particular state can have an infinite number of vector representatives. So as the output state is directly depending on the input vector representatives, the output state is also no longer uniquely defined in terms of the input projectors. So in spite of switching to projectors, we have not yet solved this problem. So the approach which we will now take is that we will relax the definition of superposition. So we will now consider the entire family of states, P alpha beta psi and exp I theta phi, where theta belongs to 0 and the range between 0 and 2 pi, to be legitimate superpositions of the states p psi and p phi. That all such vector representatives with arbitrary phase, if they give this particular output state, we will consider that to be a legitimate superposition of the input states p psi and p phi. The authors of this paper have come back to this problem again and will provide an ingenious solution. But let us now stick to this relaxation of this definition. So the first important result of the paper is the no-go theorem. What is the basic result of this theorem? That there is no non-zero completely positive map which can create a superposition of arbitrary unknown unit states psi and phi. This is the basic result. So the map, which is basically a quantum operation lambda, we are entering as the input P1 Kronecker product P2, where P1 and P2 are the input states, which are basically the projectors. And our target is to get the output projector in terms of capital psi. But the theorem is saying that there is no such quantum operation which will be able to create such superposition where the input states p psi and p phi are completely unknown. This is the main important point. The input states are completely unknown. We have no idea what those states are, and there is no universal superposition machine which will create superposition of two completely unknown states. This is the main no-go theorem. Now there is a quite lengthy proof of this theorem. I will not discuss the proof, but I will discuss the basic elements of the proof to give the idea of the basic concepts which were used to prove it. And for that, I will require a short mathematical digression. So let's discuss for once the concept of convex set and convex combination. So if S is a vector space over real numbers, so a subset C of S is convex if for all x and y in C, the line segment connecting x and y is included in C. This is the definition of a convex set. And now a convex combination is defined as it is a combination of points x1, x2, xn with corresponding coefficients alpha 1, alpha, corresponding non-negative coefficients alpha 1, alpha 2, alpha n, where the sum of the respective coefficients is 1. This is the definition of a convex combination. So now comes an important definition. Any point of a convex set that cannot be written as a convex combination of different points of the set is known as an extremal point of the set. This is a very important definition, as this notion of extremal point is a very important factor in the proof of this no-go theorem. So if we apply this concept to density matrices, let's say what we get. So given two density matrices rho 1 and rho 2, one can always construct another density matrix, another valid density matrix as a convex linear combination of these two matrices. So you see a convex combination is constructed, and that gives another valid density matrix that can be easily checked, that it is also positive semi-infinite. Trace of rho will be equals to 1 because trace of rho 1 and trace of rho 2 is individually equals to 1, and lambda plus 1 minus lambda is also equals to 1, and obviously it is also Hermitian. So a mixed state density matrix, this is what does this imply? That a mixed state density matrix can be expressed in infinite variety of ways. So a particular mixed state density matrix has an infinite number of possible ensemble decompositions. So the respective probabilities and the respective states which correspond to a particular density matrix are not unique. Infinite number of decompositions are possible, as all such valid convex combinations will give rho lambda. So this is valid for mixed states, but pure states are an exception. If we consider a pure state density matrix, rho equals to k psi plus I, then, and if we consider any such orthogonal vector, all such orthogonal vectors eta, which are orthogonal to psi, then let's say we take an inner product with an expectation value of rho between the states eta, that will give us 0, as it is evident, because eta psi is 0, eta inner product with psi is 0. And if we substitute the convex combination in its place, we can see easily that this will be satisfied only if rho 1 equals to rho 2 equals to rho. That means a pure state density matrix can never be expressed as arbitrary combination, arbitrary convex combination of any other density matrices. It has got an unique ensemble decomposition. So this is basically a mathematical manifestation of the fact that for a pure state, we exactly know the state of the quantum system, while for a mixed state, we do not know the exact vector state of the quantum system. This is the mathematical manifestation of this physical fact. So again, a few more definitions. A subset C of a vector space V is a cone if for each x in C and non-negative scalars alpha, the product alpha x is in C. And then we specialize to the convex cone for which alpha x plus beta y has to belong to C. And it can be shown that the set of non-negative linear operators of a finite dimensional Hilbert space form a convex cone. And what is the ray of a convex cone? It is any set of the form AP where A is a non-negative real number. This set is also called the ray through point P belongs to C. So if P is the point in a convex set or a convex cone, then all such points which are multiple doesn't mean integer multiple, any product where A is a non-negative real number, all such points form a cone. And again, we come to the definition of an extremal ray. A ray is called extremal if none of its points can be written as a convex combination of 2 points not belonging to the same ray. So, for an illustration of this, let's see the convex cone. So, let's say a point X belongs to C lies in an extremal ray of the convex cone. So, what does that imply? Let's say we have 2 points, x1 and x2, where x1 plus x2 equals to x, and both x1 and x2 belongs to C. So there exists non-negative scalars lambda1, lambda2, such that x1 equals to lambda1x, x2 equals to lambda2x. So that means x is related, x1 and x2 are both related to x by some multiple. So what does that imply from the previous definition? X1, X2, and X, all these points lie on the same ray. They do not lie on different rays. If the point X would have been expressed as a sum of points X1 and X2, where X1 and X2 do not belong to the same ray, then these points would not have constituted an extremal ray. For an extremal ray, a point on that ray can be expressed as a sum of other points which are also on that ray, but not as a sum of other points. So that is the definition of an extremal ray. And as we just saw, pure state density matrices cannot be expressed as a convex combination. So we say that the density operators corresponding to pure states are the extremal points of the convex set of density operators. So from the definition of ray, we can just multiply a real number lambda with rho, and so we get the corresponding extremal ray. So all such pure state density matrices multiplied by lambda, where lambda is a real number between 0 and infinity, they describe an extremal ray of the cone of non-negative operators. As we saw that the non-negative operators form a convex set, and so the operators of the form lambda ket psi bra psi, they form an extremal ray of the cone of non-negative operators. So in the proof of no-go theorem, what did we require? We required that we will enter P1 cross P2, and the map lambda will act on P1 cross P2 to give the output projector ket psi bra psi. Now, since the operators lambda ket psi bra psi belong to the extreme ray of the cone of non-negative operators, which I just showed, then they cannot be expressed as a sum of points belonging to other rays. They can be expressed as the sum of only points belonging to the same ray. So all the terms in the sum, vi rho, vi dagger, all the terms in that sum have to be individually proportional to ket psi bra psi. This follows from the extremality condition. Because if they are not individually proportional, that would imply that these individual terms belong to different rays of the convex set, which is not allowed, as this is an extremal ray. So all these terms are individually proportional to ket psi bra psi, and this reduces the complexity of the proof at one go, because now we do not have to investigate all the possible terms of the sum, but we can investigate the action of only one linear operator vi. That sum we no longer have to consider. So the proof will be now to check whether an individual operator vi is possible, which will give us the desired result. But the answer is negative, that such an operator v does not exist. So this is the what we wanted to prove, and this is what is shown, that in the qubit case, only operators V that satisfy the above condition are null operators. So such a universal quantum superposition map does not exist, which creates a superposition of unknown quantum states. So this is the first main result. But what about partially known states? So what do we mean by partially known states? Let's say we have some knowledge of some referential pure state p chi. What we mean by partially known states is that the states which we want to superpose, psi and phi, they have got some non-zero overlap with the vector representative chi. So this is what we meant by partially known states. So the above proof showed that a superposition map is forbidden for entirely unknown states. But if we have some particular knowledge, partial knowledge to this overlap, then is superposition possible? Now, as we discussed, the superpositions which are generated are not unique because they depend directly on the vector representative. So we have to specify while constructing a particular map or an operation that which particular superposition we want to generate. And so in the paper, the authors chose this particular superposition. Capital Xi is equals to alpha chi phi, chi inner product phi divided by modulus of that inner product psi, and similar another term. So alpha and beta are the superposition weights, and these are the additional factors. The importance of the additional factors is this: due to this particular combination, it turns out that the vector representative capital Xi, which is the output vector representative, changes only by a global phase if any of the individual input vectors, psi and phi, which we want to superpose, and chi, which is the referential vector representative, gets multiplied by a phase factor. So if we multiply with arbitrary phase factors any of the input states, that will change the output state only by a global phase. And so the arbitrariness which we had previously discussed, that problem of definition is now gone with this judicious choice of the superposition. So this is the superposition which the authors targeted to generate. And so the result is also stated in the form of a theorem. So here C1 and C2 are the overlap of the input states with the referential state p chi, and this is the theorem says that it is possible to have a particular completely positive map lambda sub which generates this particular superposition for fixed overlaps C1 and C2 of the input states with the referential state. And also for implementing the superposition, we require another qubit mu, which is in the state alpha 0 plus beta 1, where alpha and beta are the superposition weights of the particular components psi and phi. So this qubit mu encodes the superposition weights which we want to superpose. And also the CP map is unique up to scaling. So this is the only possible map which generates this particular superposition, given these are the overlaps and given that this is the superposition which we want to generate. So what are the steps of the superposition? We auxiliary normalized qubit vector is defined, which carries the overlaps root over C1 and root over C2 as coefficients. And then the superposition operation corresponds to 4 steps. In the first step, these steps are written down. So in the first step, that S represents a swap operator which swaps between two qubits. I is the identity operator, and 0 and 1 are the orthonormal basis states with which we are familiar. In the second step, also we perform another projection to the state chi for the third part of the whole system. In the third step, there is also a projector P mu acts on the first part of the system, while the second and third part of the system are there is no action, so it's an identity map. And in the last step, we trace out the first part and the third part of the density matrix rho, and we obtain the required output. So when I mention the first part and third part, second part, these are the respective parts. To the lambda sub, the input is P nu cross P psi plus P phi. P nu is the first part, first channel. P psi is the second channel. P phi is the third channel. The output superposition is generated in the second channel, while the first and third channels are traced out. This is a diagrammatic representation. So the black boxes at the end of the first and third part, they signify that those are being traced out, and to the second part, we are obtaining the output. So as we know, for the probability of success, we have to calculate the trace of the quantum operation. And so this is given by the following formula: C1 C2 by C1 plus C2 into n psi square, where n psi is the norm of the output state. So this formula is pretty much according to intuition, because it shows that higher the overlap with the referential state, greater is the probability of success that this particular quantum operation will generate the particular output state. So as you can see, just like any other quantum operation, this is a probabilistic operation. So implementing this quantum operation does not guarantee that as the output we will get the desired superposition state. We will get in some cases, we will not get it in other cases, but the probability with which we will obtain the desired output is given by this. It is directly proportional to the overlaps with the referential state, and also directly proportional to the norm of the output vector. And also the Krauss operators satisfy this following inequality. So the probability cannot be increased by arbitrarily scaling the operation, by introducing any such coefficients and designing like that. Due to this inequality, no scaling up of the probability can be done. This is the maximal probability of success, which can be achieved using this protocol. But this protocol is designed for arbitrary superposition weights, alpha and beta, which we do not know beforehand. But if we restrict the possible variation of alpha and beta, if we fix them, then more efficient protocols are possible. That is beyond the discussion of today's talk. But for arbitrary alpha and beta, only this protocol gives maximal probability of success. So the protocol is basically defined by the two parameters C1 and C2, which are the fixed overlaps. For each fixed overlap, a particular instance of the protocol is designed, because the qubit vector mu, which I showed, you see that carries the overlaps. Those are initialized using this overlap. So for each particular case, we have to know the overlap and initialize it accordingly. So each particular value of C1 and C2 is a particular instance of this protocol. So those define the protocol. And if we have fixed C1 and C2, then that particular instance of the protocol works not only for C1 and C2, but for all such values lambda C1 and lambda C2, but the limits on lambda are given. And in that case, the probability is multiplied by a factor of lambda. So, but in other cases, we have to again redesign and reinitialize C1 and C2 to create another instance of this protocol. This protocol can also be generalized to superposition of D states. Here we superposed only two states, psi and phi. It can be generalized to superposition of D states, and the generalization is very straightforward. So there is no other intuitive or no other non-intuitive figure here. It's a very simple generalization, and the particular output state which we want to obtain is generalized in the exactly following the state which we generated in the last instance. And I will end this with a discussion of a partial subversion of the no-go theorem. So we proved that for arbitrary unknown states, a universal superposition protocol cannot be designed. But let's say we have two vector representatives, psi, chi, and also phi. So psi has overlap, fixed overlap 1 by root 2 with chi, which is the referential state. And the remaining part is, of course, perpendicular to chi. So we represent both the states, psi and phi, in this form. And then lambda sub outputs a state having the vector representative capital psi is equals to chi plus half psi perpendicular plus phi perpendicular. Now you see it is possible by using another qubit, another ancillary qubit, to entangle the two parts of this superposition, chi and psi perpendicular plus phi perpendicular with other qubits, and then carrying out the measurement in those bases, we can separately obtain these two parts. So I am not going into detail how we can separately obtain these two parts. One part is chi and another part is psi perpendicular plus phi perpendicular. But we can separate these two parts and separately obtain these two parts. And if we obtain the part psi perpendicular and phi perpendicular, we can see that we have obtained a superposition of those part of the unit state of the state vectors which were completely unknown to us, because only the part which overlapped with psi was partially known. But using this particular protocol, we can also obtain in a roundabout manner a superposition of those states which are perpendicular to the referential state chi. And that is with non-zero probability, which in this case is greater than 1 by 4. So this protocol can be used to partially subvert the no-go theorem, which was proved earlier, though a direct subversion is not possible. So this is a very interesting result, that what we proved earlier can be partially subverted using the protocol which has been designed. So there have been various experimental implementations of this protocol, very successful implementations of this protocol using superconducting qubits, photonic states, NMR qubits, etc., etc. This was the figure which is shown. This was probably the first successful physical implementation of this protocol, and so it realizes the superposition of two photonic quantum states which have some non-zero overlap with the horizontal polarization state of a photon H. And fidelity of the output state signifies that how close is the output state to the desired superposition state. So it is seen that it is very high. So the experimental realization of the protocol works extremely well. And this is not only for this particular physical implementation, all the physical implementations which have taken place after this experiment, in all cases, this protocol has been extremely successfully implemented. So that's that. So the basic takeaways are that generation or designing of a universal protocol which generates superposition of unknown quantum states is forbidden. But partially known quantum states, we have a probabilistic protocol for generating their superposition. And if we restrict the domain of input states, that is, fix the superposition weights alpha and beta, then even more efficient protocols can be designed, and the utility of such superposition protocols, they might find extensive use in the designing of quantum computers, and they are already being used in various experiments of quantum optics. So that's that, and thank you.
Thank you, Sagnik. So, is there any questions? Time for some questions, probably. Okay, I have a question. So, you're talking about this probabilistic approach to, like, probabilistic protocol to make some superposition, right? Is
Yeah.
there any upper bound on the probability? Because there was this formula, right?
Yes.
C1, C2 by C1 plus C2, something like that, right?
Yeah.
So,
So this protocol has been designed, of course, only for uh, creating this particular superposition state, psi.
yes, right, exactly.
So for this case, if our target is to generate this superposition state, then it has been told this is the maximal probability of success. It cannot be increased because this protocol is unique.
No,
No
I
other.
get it. But C1 and C2 are just numbers here, right? So, like,
Yes.
that can have, like, I don't know, half and half, if that is the, I don't know, overlap. The C1 and C2 was the overlap, right? With the partial uh, state. So, if that is half and half, and the denominator
No,
it's
if
one.
so that is basically another minimization problem. That means for which particular overlap, which particular amount of overlap C1 and C2 is the probability of success maximal. So
Exactly.
that is
So yeah.
so that calculation can be done. I don't know whether it has been done, but that is not a very useful quantity, because as I said, that a particular instance of the protocol is defined for fixed overlap C1 and C2. So for various, so for the two states which you want to superpose, you will have only one particular C1 and C2, and for that there will be only one probability, and for
Okay.
that there is a scaling which is limited by this lambda,
Right.
multiplication by this lambda, where this lambda can vary only in this range. So for each particular instance, there is a maximum probability which cannot be increased further. But asking this question in general is a different minimization problem, which I am not sure whether has much physical significance or not.
Right. Understand. Okay. Thank you. Okay. So, are there any other questions?
I have a question.
Okay,
So,
please.
So Shagnik,
Yeah.
so are those ancillary states that you talked about, the ancillary states chi, I suppose? So, do they affect the outcome in any way? I mean, of the quantum operations, outcome of the quantum operations?
No, they do not affect the outcome of the quantum operation, at least in this particular protocol. So the particular thing about ancilla qubit, while we are, let's say, experimentally implementing some particular protocol,
Yes.
is this that so when we are experimentally implementing, we might face several hurdles in general. So how to deal with those hurdles in terms of ancilla qubits in particular case is a problem of the experimentalist. But here, when we are theoretically representing a particular protocol, this we do not go into any detail about ancilla qubits. We are assuming that this is the algorithm, and what will be the particular ancilla qubit in which particular case, how it will vary, how to manage that, that is much more of an experimental problem. Here, what we are designing is that whatever remaining is left, we do not care about that. That is embodied in that qubit. The protocol only has to ensure that the principal qubit is in the desired state. Whatever state the ancilla qubit takes does not matter as far as theory is concerned.
Okay, so but experimentally, so the ancilla qubit, can it cause, suppose, any interference on the outcomes? So
No,
I mean, is it
interference
not
it cannot
important?
cause.
Okay,
Interference
okay.
it cannot cause. But like I said at the very beginning, when I was discussing no cloning, so the ancilla state chi, for example, in this unitary quantum adder, the case we discussed, that I said that what particular value chi will take, that may depend on the input states, the states which we are wanting to superpose. That can vary from case to case. But we are not actually interested in that. Of course, experimentally, it must be ensured that the result of the ancilla qubit, the state embodied by the ancilla qubit, must not in any way affect the result of the principal qubit. That obviously has to be ensured, otherwise the whole algorithm is destroyed. But what happens to the ancilla qubit in itself is not a question of interest theoretical. So experimentally, as I am not an expert on this, I cannot comment on what are the particular problems and what are the particular ways of dealing with this.
Okay, fine. I have just one more question.
Yeah.
It's basically a follow-up question to Anirbanda's question that he asked in the beginning. So, what would happen, like, if we have, suppose, a quantum NOT gate? So, in that case, is it an example that we won't have any ancilla qubit thing because there is just one input and we'll just get one output?
Yeah, definitely in that case we can have. I mean, an
There a
ancilla qubit.
quantum, is there a quantum not gate?
No, I don't know. I'm just surmising
No,
if it
quantum
exists.
not gate is not there.
Okay. Okay.
The answer in general to your question is that there can be operations where pretty simple operations where it's a 2 qubits and the output states of 2 qubits are important to us. And the algorithm is designed in a particular way where we get the respective important outputs on 2 qubits. See, the ancilla qubit is not a necessity. The ancilla qubit, in some cases, it is a necessity. That when does the ancilla qubit become a necessity? Let's say in some step of the algorithm, we require a particular extra qubit for carrying out that particular state. But after some states, when we finally reach the output, that state has become of no importance to us. For example, here, while giving the input, we require 2 qubits, psi and phi. Otherwise, we cannot give the input. But in the output, only the output state of one of the qubits which encodes the superposition is important to us. Then the other is practically defined as ancilla, which is of no longer any importance to us in analyzing the output. So,
It's just
of
a
course,
buffer, so to say.
buffer. So, if you can design any such operation where throughout the whole process, all the qubits are equally important and no other extra qubit is required for implementing any particular step, then for those particular algorithms, the concept of ancilla qubit will not be necessary.
Right. Okay. Okay, Sagnik. Thank you.
Yeah, welcome.
Okay. Are there any more questions? Okay, if not, then let us thank Shagnik for this very nice talk. And Shagnik, will it be possible to put this slide in the drive link? Then we can share it
Yeah,
with everyone. Okay, okay. So that would be one thing. And I think today's session has been recorded. So if the audio and video quality has come properly, then we'll share with everyone. Share it with everyone. Okay, thank you, Shagnik. Thank you, everyone. So we'll meet after 2-3 weeks after the pujo probably. and then we'll have a new topic. Thank you, Shagnik. Thank you, everyone. Thank you.
Thank you, Shagnik. It was a nice talk, and thank you, Anirbandha.
Thanks.
Thank you.
Okay, bye.
Okay, bye.
Bye.